Welcome to the Plaiground podcast, AI's place to play. In this episode, we are delightful to have Benjamin Sanchez with us. Who is Benjamin Sanchez? Benjamin Sanchez is a research scientist inside at Google Research. He got his PhD at Harvard on quantum chemistry. However, a remarkable amount of his research gravitated towards AI. In particular, one of his most cited papers is on the development of an AI strategy for drug discovery. That is an amazing work. A breakthrough in AI application in chemistry. And we are going to be able to talk with his author. Welcome to the Plaiground podcast, Benjamin.
Hey, how's it going? How's it going, Miguel?
I'm very good. Well, it's a little bit hot here in Madrid. How are you?
I'm currently in Cambridge. It's also getting hot, COVID times.
Coronavirus!
So, it's a crazy world out there. Lots of stuff going on.
So enjoying, you are enjoying outdoors nowadays, right?
It's a hard time also, right?
Coronavirus!
So,
Sure.
for a lot of people. So
It is. So let me break the ice a little bit with it sounds a little bit silly, the question, but it can inspire people. So in terms of sci-fi movies or TV shows, which one do you feel that inspire more the work that you are doing on AI?
I don't know. I think I normally don't find inspiration from movies on AI. Like I think I see as AI as just like a tool that can help you do things faster or sometimes better. And if you're thinking of solving a problem, sometimes it's a good tool to have. So normally I don't think about it so much in terms of movies or sci-fi. If you ask me what's my favorite sci-fi movie, I would probably say, that's also a hard question, but I guess, I really like Inception. I really like even the Steven Spielberg movie, AI. Although it's not so much about AI, but it's I like that one, and I recently saw Dark, which is pretty awesome on Netflix. It's not a movie, but it's also very sci-fi.
Dark, the TV show.
Yeah.
Aus welcher Zeit bist du?
Die Frage ist nicht aus welcher Zeit, sondern aus welcher Welt.
Exactly.
But did you watch the third season?
Yeah, in one day.
So in one day, I have to say, because it came live like 2 days ago, right?
Yeah. Yes. It was a good day.
Long weekend, long weekend.
It was a good weekend.
Yeah. So I was planning to do the same, but I have a daughter.
Yeah.
Okay, so let's go to your work. So your work with organ, spelled ORGAN. So it's like organ, right? But so what is organ?
Yeah. So this is work I did during in the Lanas Puruguzik group, and at the time, so. And we're working with molecules, and often the space of possible molecules is huge. So you can sometimes brute forcing generate all possible molecules. If you think about you can think about them as Lego pieces, where you're adding one Lego piece and adding another one, and you can think about all possible ways that you can add these Lego pieces. Sometimes if your Lego pieces are small enough, if you're just thinking about atoms and bonds, the number of possible combinations is extraordinarily huge, right? It's you can't actually enumerate it. I mean, you can enumerate it, but you can't do it in a reasonable time. So you wanna if you wanna generate new molecules, sometimes the space that you want to explore is too big. So you need a smart way of exploring the space. And so one way that we represent molecules inside of the chemoinformatic world is as text strings. So it's so you can think about like a very simple molecule like water. Water has 2 hydrogens and 1 oxygen. And SMILE string you just represented was an O, which means oxygen. The hydrogen is implicit. And if you have something has a bond, like a carbon bond, you write a C and then a C. And so in this way you can represent a graph, a molecular graph, as a text representation. And so we leveraged the technology that was around at the time for creating text. This type of technology is recurrent neural networks. Now, if you were to do that, you could use a transformer. But essentially, we took this idea that let's use recurrent neural networks to generate text. In this case, text represents molecular graphs. And let's generate a GAN. A GAN is this idea where you have a competitive models. You have something that is generating data. Because there's no guarantee that this data is actually going to be nice or actually look like the data that you want it to look like, you need something extra, and the extra is having a model that tells you it looks like it or it doesn't. So this is the discriminator model.
It looks real or it doesn't look real, right?
Yeah. In this case, you have your data, which are molecules, and you want to get a sense if these molecules look like real molecules or fake molecules. Real in the sense that they look like the same type of molecules that you gave it. Do they look like they come from the same family, from the same bag of molecules? So you have a model that's learning how to generate stuff. You have a model that learns how to tell you yes or no. And this will already generate molecules. But often, you also want molecule to have certain types of properties. So if I'm building a solar cell, an organic solar cell.
So let me ask, exactly. Yeah. Okay, so I was about to ask you probably that, and I interrupt you, sorry. But so when you are generating a molecule, you are simulating a structure of a molecule. So applications in pharmaceutical and new materials are clear, right? For new materials.
Yeah, everything that is made out of molecules, you can think about it in this way, right? Obviously, in some cases, it doesn't make sense to think about molecules, but more as a materials on a bigger scale.
Mm-hmm.
And in that way, you might want to represent your data in a different way. We're looking at only molecules in the very, at the atomic level, right?
Sure.
Yeah. And I mean, maybe I'm getting all around it, but just to synthesize, ORGAN is an algorithm for generating molecules using GANs and reinforcement learning. I sort of described a little bit the GAN part. This GAN part generates stuff that looks like it. But often you also want things that have certain properties. In the case of molecules, you may want your molecule to be soluble in water. So that's like an extra constraint that you have on the system. You only don't want molecules that look like drug-like molecules. You also want them to be soluble within a certain range. You might want other properties. If you could actually predict the price of molecules, you might want to say, I want cheap molecules, because those are going to be easier to make. So you can imagine for any material problem, solar cells, batteries, pharmaceuticals, even if you're making a pharmaceutical, you're typically thinking about a specific type of, targeting a specific application, right? Like a disease. So if you have a way of putting a number on any of these desired qualities that you have on a material, you can use reinforcement learning to sort of bias your generation process towards those constraints that you have. The whole idea of reinforcement learning is it's you can think about, in this case, your generator, your algorithm that generates molecules, as like a player in an environment, and it can make decisions. These decisions can be: should I add an atom here? Should I add a bond here? Should I make this edit on a text representation of a molecule? And based on this like decision space, decide what is actually going to optimize the constraints that you initially are desiring, right?
So the reinforcement learning part is built after the GANs generate a simulated molecule, right?
And in this case, we're actually doing training at both at the same time. It's
so both at the same time. So you transfer what the transfer learning get at the training part. You transfer that information also in the training of the GANs, right?
Yeah.
Man, that is super sophisticated.
No. I think it's more like, so if you think about images, we tend to model them as like continuous variables, right? Like you get like a pixel is like you think about it as a continuous variable. It's something that you can vary from 0 to 255 or 0 to 1, and you can always quantize it at some way. The problem with strings and with text is that it's discrete. So because it's discrete, it's actually propagating gradients is kind of hard. It's a sampling problem. So you can't do a lot of, like, GANs came out for images in 2014. For text, they didn't come out until way later, and they actually came out with a work called SecGAN that kind of cast the GAN problem as a reinforcement learning problem. So, and the reason why you can only do this GAN game with using reinforcement learning is because you can't propagate gradients, and this when your action space is discrete. So like essentially what we're doing is we're saying, look, we're always going to use reinforcement learning in this discrete space. The part that we decided was like, actually, there's a part that you care about, the GAN part, but you also care about these other things. So actually, let's add these things into the optimization procedure. So that was more the part where we decided to that was more our contribution, right? Like people were already doing GANs on text or the sequences, and they were doing it with reinforcement learning because this is the only way to propagate gradients. There's a technique called policy gradient, which allows you to estimate a gradient in this discrete spaces where you can't get gradients, or nice gradients. But if you're doing reinforcement learning, you can make your objective you can make it very complex. And so instead of having a GAN objective, which is it real or fake, let's have that as a constraint, but let's add more constraints about things we actually care about. So it's a little bit like, let's put these things together.
Yeah, but here is the point. So Gann's paper from Ian Goodfellow was published in 2014.
Yeah.
So reinforcement learning became hot in the industry in 2016, 17, right after the publication of the AlphaGo results.
Yeah.
With also combining with deep learning. So, and your paper was published in 2019 or 18?
Yeah, around that time. Yeah.
So basically, I mean, you just jump into the game with the paper. I mean, because you published the paper in 2019, but you start working on that previously. So it was. I feel that you were using these new technologies when they were still fresh or fresher than today's.
Yeah, I mean, I think I think in the lab I was in Alan Aspurguzic's lab, we had a lot of I mean, the philosophy was always like, let's try to solve problems, and we were always listening to what was happening at the moment, and the I think the part of like the idea was let's we were very free in trying ideas and trying out new things, and so and I think a lot of it is also very helpful that the machine learning community is very like pro open source, right? So if you have a new idea, you get out there, you make a preprint, you submit it to conferences, and you make a GitHub repo. And not always is it replicable, not always is it easy to, because everything's moving so fast. But at least there is like some tidbits that help you to reconstruct and actually build on it, right?
So how important was, you mentioned it, how important was the fact that all these new technologies, like we are talking about algorithms, right? But at the end they are materializing code that are very well written, documented, using different multiple examples, and that is free. You can use it, you can fork it and and start using it. So how important was that in the elaboration of this work?
I think it was very important. We were because we were building off on like a very recent work that like introduced GANs to the sequence modeling, which was SECAN, and they made their code implementation available, and because of that, you're able to, and if you read the paper, you might be able to reproduce it, but I think it takes a lot of time to actually like learn how to do that, right? Even like if you're an undergrad and you just read the paper, it might be hard to actually reproduce it because it's just like there's a lot of ideas. This is something that would require you like several ideas to even get it to your and here's somebody that is putting their code online, and it allows you to also get a sense of how they're thinking about it, how you translate what you write inside of a preprint into like a published article. How do you materialize that into code, right? Because there's always some technical aspects. There's some things that relate more to the programming language. So like it really helps you to bridge like ideas that are sometimes are more theoretical into something that is very concrete. And that's also how you learn, right? Like if you wanna try a new idea and you wanna build off on research that is happening, it's a really that's one way that you can learn how to like make your code better, how to leverage all these and it's just not looking at one implementation. You can look at several implementations and get a sense of how other people are also translating the same idea into a different framework.
I mean, it is an increase on speed that, to my point of view, because actually we are using this type of technologies in the business. So it is a change in the paradigm. From the point of view of competitive advantage, when you're talking about, okay, I'm using AI that nobody can use it, but if it's open source, and there is where people somehow are developing the next breakthroughs, or it's easy to replicate that in the open source community, the new breakthroughs. So there is no competitive advantage in terms of technology for the business.
Yeah.
In that sense.
I guess the only thing that you have to be careful when you're looking at stuff is like, GitHub repos is like often the models will also have errors that, are from the researchers, or if you're looking at data and there's biases inherent in the data, you're sort of inheriting these biases and these errors. So, it's always important to like be aware that you're inheriting, problems that you might not think are there, but might be there. Just like if your model is trained on a particular data set, and there's biases in that data set, your model might inherit those biases, and you might not know that. But that's why if you're more open about your model, and one way is being about code, but also analyzing and doing sanity checks on them.
Let's put it this way. So you have to be extra careful on this, on checking the code for these biases, because you didn't write it. You didn't write it for the purpose of another application, and so of course there is a difference with writing from the beginning, right?
Yeah.
Coding from the beginning,
Yeah.
something. There is a huge difference, but you have additional problems in this sense, right?
Yeah. So it's not perfect, but I think it's you got to do your due diligence. Like
Exactly.
Yeah, like and you should do that even if you're coding it by yourself, or if you're like inheriting or using building off on somebody else's work.
Mm-hmm. So let me ask you one thing. So in the drug discovery community, were you guys pioneer in using this strategy for drug discovery?
Yeah. So I think I think on the drug discovery front, when we were developing this work, we were mostly thinking about possible domain applications. And if you're thinking about molecules, like one of the biggest industries is going to be pharmaceuticals, right? People care about their health, and so it makes sense that you want to create drugs and treatments that improve people's lives. So we're looking for applications around that. We actually in the lab I was working with, we didn't focus too much on we didn't have that many collaborations, so we didn't work that much in the drug space. Because the drug space is huge and it's complicated, and there's a lot of levels to it. Not just molecules, but even the biology. Even there's a lot of spaces.
Clinical trials and all these things.
We actually worked more on the organic material space, so batteries and solar cells, and we were but a lot of the tools that you develop. What happens often in chemoinformatics is if you develop a tool that works sometimes for one problem, and it might be useful in other domains. And so, it's important to always contextualize your research in a area where it's going to be useful. And so we had this we had this algorithm, and we contextualize it. Okay, so if you were using this for drug discovery, what are some things you want to do? And of course, you can't cover all of them, and we did not cover all of them. There's a lot of new research that has come out, and there's a lot of critiques about using these type of algorithms in the space. And so saying we discovered a new drug, we didn't do that. There's people that have done that. But it's mostly that we introduced this idea of combining these things, and that you can do that in the drug discovery space. The actual process, there's always a huge gap between the idea or starting with an idea and then actually getting into production and actually solving the problem that you're setting out to do.
Correct. I mean, this space is extra hyper regulated, and it's hard to come up with a new technology that, let's say, that you cannot explain in the way, the outcomes you cannot explain in the same way that you traditionally do. And of course, you speed up the process of some of the stages for a drug discovery or a drug coming to the market, but still, that is a extremely slow process with millions of money spent, so very and efficient, let's say. And for example, nowadays we are in a rush with the pandemic for this type of I don't know, technologies to speed up process.
Exactly. Like it's
So what are the critiques that you guys were talking about when you were bringing this new tool?
Yeah, so one critique can be like, you generate a molecule that has the properties that you want, but it's just an idea. You need to convert this idea into something material. If you give me any arbitrary molecule and actually converting it into something material, well, you have to figure out how to synthesize it from maybe a natural product. Figuring out the synthesis route, all the steps that you need to make to transform something natural into whatever you discovered is hard. And even if you do it, there's a lot of engineering aspects of how to actually optimize this in a way that is cheap. So even getting it to something material is hard. You can have a PhD student figuring out this, working an entire year just to figure out how to do it. So that part is hard. So, even if you have the idea, you still haven't solved the problem. You still have to go through this trial. So that's one aspect. The other aspect is it's not clear to how to evaluate these models. If I have my algorithm and you have your algorithm, how do we say one algorithm is generating better things? It's hard because the actual truth is in the experiment, which is really expensive. And if you really want to make a strong claim, you need to make it a statistical claim. So that means you need to run several experiments. So it's very expensive to do all of this, actually. The other critique is that if you really care about solving a problem, maybe the best way is you don't need to generate new ideas. Let's grab the catalog of things that we can buy and just start there. And let's brute force our way through this catalog. There's like internet, there's companies that specialize on building these catalogs. You might have a catalog that has 200 million molecules. It's a fraction of the entire space of possible molecules, but it is a space that you can achieve. You don't have these constraints of how do I get here? How do I make this molecule?
So I assume that catalog come with the instructions to synthesize the molecules, right?
Well, it kinda. It's like you use very simple reactions or chemical transformations, and so you can get there in a reliable way.
Okay.
It all depends where you're buying the molecule or who's making it. But
I mean, I see the challenges there and the question in this type of things, but still I think it's useful. Let me ask you one thing, because following the same thought process to use GANs and reinforcement learning to generate new molecules, would you or have you think about on using AI to also given a molecule with certain structure and all the precursors of synthesis and the steps that you can do, you can classify that, right? You can categorize that to get an AI that give you the instructions to build a molecule. I'm sure that you thought about that.
Yeah, I haven't worked in that space, but because that's a whole set of problems. I mean, it's a whole subfield which is around synthesis planning. But there are people that have done that. I have colleagues that have done that, and I haven't got into that because I've worked more on the part of how do you predict things and how to generate things. But yeah, there are now people that there's people at IBM, there's people at Google Research, there's people in that have worked on that, and there's there's several research groups all around the world that have done this.
And
So
from your
there are
colleagues,
already some ideas.
sorry,
What?
from your colleagues. So what is the feeling that you get from there?
I that well, it's kind of like split. I've heard people say that you can, you know, that really what it makes like it's the same problem with the generation thing. Like often, you can think about any arbitrary chemical transformation and you can think about how do I get the reaction for that? Or you could just think about what are the reactions I know are reliable. Because it's not just about the reaction, it's getting a reaction that is very efficient. And maybe instead of trying to find any arbitrary reaction, you should just focus on the reactions we know we can do reliably with current equipment. And so then the problem is like it's constrained and it's much simpler, and you can brute force your way out of it. There's maybe 10,000 reactions that you can try, and you can apply these reactions on a molecule and keep on doing it. And it might take a long time to compute, but it's something that you could compute. So that's one perspective. The other perspective is let's do it. Like the problem is that the bottleneck, first we have generation. The bottleneck is converting the idea into a molecule. Now we're talking about materializing. The bottleneck, if you can materialize a molecule, the bottleneck becomes actually making them. So for that, you kind of need a robot. You need to automate it, right? You need to maneuver in the physical space.
Wow.
So the bottleneck goes from the idea, from now planning out how to execute the idea, to now actually having to make it.
But you can have a human doing the reactions, right? As well.
You could,
Okay.
but it might be unreliable. Like
because of the number of reactions that you have to go through.
and there's a lot of there's a lot of things that can go wrong when you're actually making these reactions.
I see.
There's a lot of variables. There's the environment where you make the reactions. So if you can really systematize and really control the noise, one way that you can control that noise is using a robot that will synthesize the molecules.
Yeah.
Right? So that's the next bottleneck.
So
Getting a robot to synthesize.
Okay, let me ask you also, do you know of any startup, company, university that is trying to get to that point?
Yeah. Like actually, the lab, I was part of it. Like there's this whole vision about these are stuff that we talked about all the time, right? We know what the bottlenecks are, and so Alana Spurguzic's group in Toronto works on that. There's also Lee Cronin in the UK. He has this concept of the chemputer, so it's like computer but with chem. So they have some really interesting work around that. There's other labs that are starting to think about this. It's all starting because it's a different space. You're trying to do optimization, so you could think about Bayesian optimization, but you also have to maneuver the robot, which also needs to be calibrated. So it has a bunch of other things. If you're thinking about startups, there's one called ChemOS, which is like this idea of generating an operating system for chemical problems. There's Kibotics, which is not so much about the chemistry, like generating the software, but they're more on the side of discovering things and like getting this working on the robot. So Kibotics and ChemOS are two startups that are working on that. There's probably other ones and this is just like starting, right? There's I think the term for this is automation platforms. Trying to remember exactly what's the exact term.
Automation. Okay. That's cool. So I didn't know about these startups. I will take a look, definitely. Okay, so you are working in an amazing company with super smart people. You have been doing your PhD at Harvard. You're living in Boston, Cambridge. So, I mean, you are surrounded of really talented people. Now, I know that you also have been working in multiple Latin American countries and also in Spain for volunteering to teach and work with the future talent, right? With young talent. So, in your opinion, I know that being in an ecosystem with talent is different than being in an ecosystem that the talent is not the driving force, right? But from your experience, have you found that talent, raw talent, is everywhere?
Yeah, of course. Yeah, definitely. Like I think, I think a lot of times that talent also comes out naturally by necessity, right? Like I think when there's problems that are local, or that are in a certain scope, and you're very close to those problems, that, and when you're trying to solve those problems, that's where like the talent comes out. Yeah, I think and I participate in these things because I think you never know where you're gonna arrive. I myself wasn't like looking to work in AI. I wasn't looking to work in chemistry. I I was in my hometown of Guanajuato, and I think like it's mostly that there's there's a lot of ways that you can identify yourself with other people that are in similar positions that didn't know that that's an option. I feel really grateful working right now where I work at Google Research. I get to work on interesting problems, and we get to do research and open source or research. So I think it's like a great opportunity, and I think part of it is you also want to make local environments stronger, right? It would be nice if you could do excellent research irrespective of where you come from, and they could be everywhere. There's some of those limitations are resource based, and some of them is just like you need good mentors. You need somebody that can help you and guide you and give you ideas, and and that's why I think it's important to like engage with like communities and Mexico, and the way that I have engaged is with like science clubs Mexico, Bolivia, Paraguay,
Colombia, Peru,
Colombia, and Spain, right? And
yeah,
and so I think it's like like there's I think I for me when I was studying undergrad, I wanted to just do video games. And it wasn't until I had other experiences outside of my local environment that I realized that you can use mathematics and computer science to like solve. You can use these as tools to solve problems that are very meaningful to a lot of other people, and that are useful for communities and places and other places. And so, and so I think sometimes you need some like intervention from somewhere else to shock you, and also like find that inside of yourself. And so talent, there's everywhere. There's a lot of potential, but you kind of need to shake things up so that you can figure that realize that potential, and bring it out and make it flourish.
Sure. So I think it's critical to expose to that talent in an early stage of their life, to things that help them visualize what they can achieve. And the closer that you get to that, and it's very simple to exemplify that with soccer. So if you want to play a soccer player, if you want to be a soccer player, and you have the chance to train with Leo Messi or with Cristiano Ronaldo, that is a life-changing thing, right?
Yeah. Yeah, and sometimes it's not so much about the skills you learn, like
Hmm.
what
The
you learn
inspiration,
from.
the inspiration.
Yeah,
Yeah.
it's just like maybe realizing that Messi is just somebody like you. I don't know Messi, so I don't know if I could say that, but I think sometimes it's yeah, just like identifying with somebody, and sometimes that has to be that has to be one person, but that's also why it's important to have representation.
So have
You know,
have you ever tried to teach AI in Latin America? With Latin American
yeah,
students in Mexico or Colombia or Bolivia?
yeah, I've done that in summer school during a research conference that I organized with other friends called RIA. I've done it in science clubs. In Science Clubs Mexico, I gave a workshop on discovering the Higgs boson. We took the Higgs boson Kaggle challenge data, and essentially we did a few Skype calls with some researchers that worked on the actual data and on the Higgs
Awesome,
boson.
awesome.
So they
It's
got to talk to them,
very smart.
and you know we did basic things. We did Python and scikit-learn. But I think the more important part is that they would realize that there's these tools that you can use them to solve problems. That there's data, and you need to kind of understand the data so you can try to solve the problem. But they're also very powerful tools because sometimes you can change the data set and you can still use the same tools. You always have to be careful because to actually solve a problem, you really need to know the data. You really need to know the tools. It's not like you can just throw any model at it and be sure that you're going to find the Higgs boson. But just get them, tell them like these are some things that exist in the world, and people are using them to solve problems.
Sure, absolutely. So I don't know if you are aware of this, but Andrew Ng, the co-founder of Coursera and many other things, he built a new division of the deep learning AI in Colombia.
Hmm.
So
No, I didn't
did
know
you
that.
know about that?
Oh, that's cool. No, that's
Yeah,
pretty
yeah.
cool.
So
I should check it out.
yeah, definitely. So I mean, it is. I mean, you know about the ecosystem of talent that is in Latin America, and from my point of view, it is something that he also realized that. Or I cannot find another strategic reason to do
Yeah,
that.
yeah. I mean, I think there's been some efforts to try to uh, bring AI research centers and just developing AI capacity across the developing world. You can see that because, for example, Google AI uh, the has a research center in Ghana. They
Yeah,
also started,
In Africa, yeah.
yeah, and of course Africa is huge. So this is just one research center. You're gonna need more to cover, like the whole more strategic areas. But it's a start. There's also a research center in India that just opened up last year. There's not there's some research centers that are national in different countries in Latin America, but there's still not a very strong concerted effort to try to create like a research center that is like Latin American based, or just like unify it. Right there are some coalitions. There's Latinx and AI, and there's also we're doing RIA, and there's also Kipu, and all of us have like similar goals. And yeah, I mean, there's a lot of potential, in part because sometimes there's solutions that are that are software based, where with very cheap hardware, if you have a really smart software, you can like leverage a lot. And a component of really smart software is maybe like an AI algorithm, right?
Yeah, definitely. So let me ask you, how cool is to work for Google Research?
Yeah, I mean, I think I'm really fortunate. I like during my PhD, I didn't know that you could work in a company and do research. I by random circumstances, I ended up applying to do an internship at Google, and I ended up working on stuff that were close to what I was doing in my PhD, working on graph neural networks for molecules. And we're working on smell. We have a preprint and a blog post out.
A smell.
Yeah, we're working on olfaction. Smell is the chemical sense. So when you smell something, it's yours. Like in the same way that our eyes are sensors for light, our nose is a sensor for molecules. So if you really want to create algorithms that are better and are able to navigate the world, you also need to give them a chemical sense. They need, imagine if you have an algorithm that works in agriculture, like in cucumbers. Sometimes you can just tell if a cucumber is good or not, or is high quality cucumber or top tier cucumber by looking at it, but sometimes you gotta smell it. So like in the same way, we're working on smell. We're working on graph neural networks.
Visual perception comes first, always. Taste and smell come second.
Or what do you mean, like come first or second?
Like when you see an agricultural product, like a tomato or zucchini, whatever, the visual perception or the evaluation visually comes first, but then it comes second, the smell and the taste.
And I think in that context, like there's a lot of, like, human beings are often, we take a lot of information visually, right? Even before any other sense. But what if you have a robot in some foreign planet, and you're looking at stuff and you don't know how to recognize that because your algorithms are not trained on a Martian floor, but having a chemical sense can tell you a little bit about what something is made out of, that you can't do with vision in those scenarios. Or, there's a lot of other cases. Like, I think ultimately you kind of want to have all senses.
Yeah. Okay, so last question. So this is the last question, and I know you are going to like it because we call it the quantum question. So here I have 10 different questions, and I'm going to use a quantum-based random generator number from an Australian university to generate a number between 1 and 10. So it will pick the question for you. Sounds good?
Okay.
I can send you the link, but probably you know that. Okay. So the number is 6. Let me go to the question.
Okay.
Okay, here is the question. So if you could ask only one question to a super intelligence, what would it be?
I mean, what is a super intelligence?
Well, it's an algorithm that Benjamin has developed and is able to answer anything with the right answer.
I don't think I could develop an algorithm like that, but if I could get it, if the question were I can ask any question and get an answer, I would ask, how do we solve climate change?
Wow.
I think that's a very pressing issue, and I think a lot of the issue is more human based. Like we know that the technology side, there's always things that we can improve, but I think it's how do we organize how do people organize to solve climate change? That would be my question, because even though we have the technology, it's like we don't know how to, and it might not be around how to convince people. It might be more how do we, because even if we actually know, like, you know, I did a specialization degree on energy and climate policy, and even though I know that, I think there's still a lot of, like, you know, there's still a lot of things about how do we organize to solve climate change.
Yeah,
I think that's the question I would ask.
Actually,
You know,
yeah. So sorry, I didn't want to interrupt you.
No, I mean, I just think it's like, you know, if there's something that's gonna not wipe us out, but is gonna impair our quality of life, and, you know, millions and billions of people everywhere, and that's gonna cause, like suffering and pain, and, you know, just general bad stuff. It's climate change, and so yeah.
I mean, it is at the same level that the pandemic that we are suffering. The pandemic speed is exponential. The climate change impact that also will shape the world is not exponential. It is slower, but probably harder to tackle.
It might be exponential, but the coefficient might be smaller, right?
Yeah. So I will not ask that question. I think it's a good one, but what I will ask is, can you solve the climate change problem for me?
The answer might just be no, and then the information is not useful to you.
Yeah. Well, then it's
or
not
you might be doing yourself.
Okay, Benjamin. So thank you so much for the time that you share with me and with us, with our audience. Thanks to our audience for being listening this podcast, and I hope you enjoy. And tell us in the comments who would you like us to invite to the show. Other quantum question for our last question, and well, I don't know if you want to close with something interesting to say.
No, I mean, thanks for having me. You know, there's, yeah, it was good chatting. Check out Clubes de Ciencia online, and also check out RIA. And, you know, if you're interested in smell and molecules, check out the blog post that we have on machine learning for scent, for smell. And, you know, yeah, and, you know, feel free to reach out.
Thank you so much, and see you in the next one, players. Until then, keep an eye on AI and stay awesome.